Okay, we're going on into lecture 3 now. We can look at odds and sample spaces. We'll also have to know what's an outcome, what's an event. An outcome is a basic single result. So, and I know this is an annoying part for some people. It certainly was for me. Trying to say, what's the difference between an outcome and an event? But an event is what we're looking to get the probability of. An outcome is when we look at individual occurrences of things that happen on their own to help build up to an event. So an outcome is a basic single result. I'll put here like one coin toss. An event is a series of outcomes. For which probabilities can be measured. Usually an event has some special description to it. You know, flip a coin. Get that done. That could be considered an event, but it's technically the shortest event possible because one thing happened and there's not going to be the series. But a series can be made up of one event. Also, technically, the shortest series possible. But an event is probably what we're going to look at. What specifics are they looking for in the event that makes it a success for what they're looking for? Remember, success can be good or bad. If you're saying success is finding that a patient has cancer, I would not call that good for them. But your search for them has succeeded in finding a person with cancer. It could also be good, you know, success is you took a basketball shot and it went in versus a failure of missing. But a success is finding what you're looking for. So it's the success of the search that we're talking about. Right. Now, this could be like the probability that a die rolls to be less than 5. Looking at the events, right? If you look at the outcome is the roll is a 2. The roll is a 4. Single roll event, single roll outcome. But the event is, let's say there's several things that are less than 5. 1, 2, 3, and 4 for the top facing face of the die versus 5 and 6, which are not. And that's where you get a probability. So events are made up of individual outcomes that can be part of succeeding or failing. Now people talk about this all the time, odds. Odds, and I'm not going to say odds are, because odds is the name of one thing. So odds is a special way to describe the likelihood of an outcome. Probability already does this. Where you have successes over total. Successful members of the sample space over the total size of the sample space. Odds can be in favor or against. And it matters. Because a probability is always about successes going over the total. Odds always compare two values, but they are successes and failures. I didn't say over. And failures is a non-success. Wins and losses come to a total number of games. Successes and failures come to a total number of outcomes that are in the sample space. We always list the type of odds value first and the other second in any odds ratio. So there's the English description of what's going on with odds. It does the same type of labor as probability, but it says it in a different way. So if you know the probability, you can find the odds in favor, you can find the odds against. If you know the odds in favor or the odds against, you can find the probability. Because what this is all based upon is that wins plus losses equals a total. That total will represent your sample space. You'll have some wins or successes, some losses or failures, and then together will get you all the way to your total. When you're using the probability, you're going to need the total and you're going to need the wins. When you're using odds, you're going to need two of these things to make sure you can get the third value. So if someone only wants to talk to you about probability and you don't know about odds, they need to give you a ratio of successes over the total. Failures or losses never come into it. What can happen now and what we have to do to get into odds is base our wins plus losses equals total to find the missing value to establish the portions, those spots that we're going to fill with numbers in a ratio. See, a ratio has one number over the other. It's not like addition, where you can add them in either order. It's not like multiplication, where you can multiply them in either order. It's very important which one comes first. So that's why it's so important that they mention whether the odds are in favor or the odds are against. Okay, now when they talk about the odds of, the odds of the Kansas City Chiefs winning the Super Bowl, if there is one in 2021, are something like 6 to 1. Well, wait, what odds? What kind of odds? Does that mean that they're going to win 6 times and only lose once? No, it actually means that they will probably, if they ran the season 7 times, which you can't do, if they ran the season 7 times, which is 6 plus 1 for 7 total, they would win one of those times. So they would have 1 win and 6 losses of trying to get to be Super Bowl champions again. What kind of odds is that? That's 6 to 1. I'm not saying it's that long odds, short odds. What they're saying is they put the 6 ahead of the 1. They said 6 to 1, and those are the odds against. So when you hear sports odds, they're almost always spoken of as odds against. So that's what's on the street. But in math, you need to say odds in favor or odds against. Just that when you're hearing things like a horse odds thing, it's almost always odds against. A few years ago, that wasn't true. When we were going to the Belmont, we had a horse trying to win the Triple Crown. Such a strong horse compared to all the others that almost everyone thought the horse was going to win. So when you bet your money on that, it came in that the odds might be something like 5 to 1 would be awesome, right? You could bet $1 and win 5, so you'd get $6 if this horse that's almost certain to win. You could turn your $1 into $6 just like that, or maybe 1,000 into 6,000. That didn't happen. The horse was such a strong favorite that the odds were not 5 to 1. The odds were 1 to 5, which means you have to bet $5. You put $5 of your own money into the pool. And if you win, you get $6 back. If that horse doesn't win, they keep your 5 to pay somebody else. So odds in favor and odds against, it's very important you know which one we're dealing with. And I want to keep this down here, that wins plus losses equals total, because that's really a big deal. I want to keep the other thing on here that's going to be a part of what's going on with odds as well. Okay? What happens is odds are going to compare two things. I'm not telling you the order right now. They're going to make a comparison between success and failure. The one that's mentioned in the name of the type of odds that they're doing is the first of the two values mentioned. So odds of 5 to 1 against means 5 is something and 1 is something. But against is first, so against is bad. And that's where your losses are. This will be your wins. So 5 losses to 1 win. What would happen if this was a bet you could make over 6 different seasons, but the odds were always the same? You would bet $1 each season, and if the team wound up winning, you would collect your 1 back, as well as the 5 that other people put in as part of the pool, and you would get $6. If your team didn't win, your 1 would stay in the pool and go to someone else. So let's say that that's the odds on your team. They're really good at 5 to 1 because there's like 30 teams in most leagues, right? Major leagues of most types. And your team is 5 to 1 is what they're playing. They're going off as. You bet it 6 years in a row. 5 years it loses, and you lose $1 each of those years. And then the 6th year they win, and you get $5 plus you get your own $1 back for not losing. And so then you broke even. And that's what goes on with odds. Of course, there's more to it than that. When you bet on sports, the people that are taking your bet need to make money. So what happens is, if they're going to pay you at 5 to 1, they actually need to keep some of the money before they pay you out, so they compute the odds or the probabilities, however you want to think of it, of what they're going to pay, in such a way that no matter who wins the bet, the house makes money. On sports betting, on horse racing, stuff like that. Because what happens is, let's say $100 goes in for people that bet on horses. They'll take about $15 to $20 out of that 100 and keep it for the house to pay their expenses, and they'll distribute the 85 that's still in there for the winners. And that's how sports betting works. Sports betting is actually a little different than horse racing. Horse racing, all the money goes in, they take their cut, and then they pay out the winners with what's there, and that's it. In sports betting, they stay locked in on this thing that's 11 to 10, right? They bet you, if you want to bet on one team and maybe they give you points or whatever's going on, it's 11 to 10. You got to put up 11 to win 10. And they try and set the line of how the sport's going to be played with extra points going to the team that's not as good, to try and draw a balance, like they call it handicapping. That's what goes on, is you've got to pay $11 to win 10 on what should be equally likely to happen. So you put in 11, and the guy next to you likes the other side of the bet, and he puts in 11. That's $22 in there. And the game is over, somebody wins and somebody loses. What happens is then they say, all right, we've got $22 sitting here. That guy did not lose, he won. He gets his 11 back for not losing. He gets 10 for winning. He's got 21, they got the extra $1. That's why it's so important in sports betting that whoever is setting the temptation by setting how many points they're going to give to the extra points to the less successful or less anticipated winner, is going to try and attract money on both sides equally so they can get their little portion of a big amount of money bet. Because think of it as if $22 million was bet on the Super Bowl in one casino, right? And 21 million of it has to get paid out to the people who get their money back for not losing, and who win, they keep $1 million. That is the goal. They don't care who wins. They're not trying to tempt you to take the loser. They're trying to tempt everyone to bet evenly, lots and lots of money, so that the amount that comes in is big and they get their percentage. But they can get it wrong. If all the money is bet on one team, and that team delivers a win for the bettors, they can do poorly. But just as likely, the team that everybody bet on could do poorly. They can make a lot of money. They don't want that. They're not in the business of gambling. That's what happens, and that's why odds are so important. So this is what that means. Odds of 1 to 5 against means 1 to 5. This is bad, so that's a loss. Odds of 1 to 5 means you're expected to lose 1 time and win 5 times, which means your team is so good that over 6 years they're going to win 5 times. And so you have to put $5 in, and at the end of the year, if they win, you get your 5 back for not losing, and you get $1. And let's say the first 5 years they do win, and every year you make $1 and you're $5 ahead, and then the next year you go up and you bet and they don't win for whatever reason. Then that year you don't get your $5 back, and that's how you break even. Again, the house is taking money in that way. So let's look at how some odds calculations are done. If the probability of a horse winning is 1 out of 6, of course, is like the side of a die, right? You roll the die, but there are 6 horses. There are horses in this race. And the way it's determined, there might be 6 horses that are each thought equally to win. There might be 2 horses, and the other horse is way better. There might be 50 horses, and this is the best horse in the race. But the probability of this horse winning is 1/6. Find 1/6. Find the odds against the horse winning. Against is important. The first step doesn't deal with against. Odds tells me I need wins and losses. Here's what I have. It does say that the odds of the horse winning is 1 in 6. So wins equals 1. Total equals 6. How many losses will there be? Well, what you do is you take losses, in this case, is the other one, is going to be your total minus your wins. 6 minus 1. L equals 5. Now they want to know the odds against. You now know wins came as 1 in the probability, total came as 6 in the probability. You do the total of all the races, get rid of the wins, and you got your losses. Finishing second is a loss. Finishing last out of 50 horses is equally a loss. There are 5 times this horse loses, 1 time that it wins. Odds against? Against is losing. Give me my lose number, 5. And since it's odds, losses and wins are getting compared. It's called 5 to 1. And that's what it means. And this is what 5 to 1 would look like, right? You might say, can't you just call it 5 because it's 5 over 1? And it could look like that. The important thing to know is if you wind up facing 51 to 1, okay, this would look like that. They don't write the 1 at the racetrack. If it's just a 5 to 1, they'll write 5. However, it will show up sometimes like this. 7 to 2. Here's a horse. 7 losses, 2 wins. In 9 races, 7 plus 2, 9 races, the horse is expected to win twice. That will show up. They can't make a fraction on the board. So it'll look like this. The really important thing is the red bulb blinking in between. That means 7 to 2. If that red bulb isn't blinking, then this horse is actually thought to be 72 to 1, which means it'll run 73 races and win 1 of them. So that red bulb is very important. That goes way back. The red flashing bulb is something that goes way back. They still use it on digitals for now. But they would write it as that. The ratio, what you hear is 5 to 1, usually be what people will say. What are the odds on that horse? They'll say 5 to 1 to each other when they're talking. But on the board, it'll only show up as 5. They don't need to put over 1 all the time, just as we don't need to put over 1 in our math. So now, let's look at this same question, same horse, all that stuff. What are the odds in favor of the horse? Odds in favor says favor, so the first thing you're going to do is favor. Wins. What are the odds? Same setup. Find the odds in favor. what we've got here of a probability equals 1/6 horse. Okay, wins equals 1. Total equals 6. Losses is everything that's not a win. Take your total minus that and get your 5. How do we get this now? Probably the odds in favor is winning, so you give him 1 first. And you don't put his 1/6, that's your probability. You got your losses right there. That would become 1 to 5. And these are the odds on that horse a few years ago going for the Triple Crown. It did wind up winning, which meant the classic bet is to bet $2. And so if you were to bet $2, you would get back 1/5 of that. You would bet $2, say, yes, I picked the winner, let me go pick up my winnings, and you go collect $2.40. But that's because they really had a lot of people expecting that horse would win. Some horses that are really big favorites don't always win. Even boxers. Mike Tyson had an issue in 1990. 50-1 favorite. They couldn't even get people to bet on Buster Douglas. So they were thinking they're going to just lose a little bit of money to each amount of money that people bet. However, people had bet millions, so they were not liking what they were seeing. And then Mike Tyson got knocked out as a 50-1 favorite, right? 50 in his favor. And they got to keep all the money that people bet, unless a few people bet on Buster Douglas, and they paid them out. If Mike Tyson was 50-1, they wouldn't be paying Buster Douglas out at 50-1 also, right? Mike Tyson's 1 to 50. Buster Douglas probably wouldn't be getting paid exactly the same. 1 to 50, he'd be getting paid like 1 to 48 or something like that. But it happens. Heavy favorites can lose. And if you're on the side where you bet on the underdog, is what they call the person who's not the favorite, then a small bet will return a big win, because all the people that thought it was going to win and didn't have any risk that they thought they were taking don't get paid because it comes to you for having bet on the underdog. If a horse is a 9-1 shot, this is 9-1 shot, what's the probability of it winning? Now, the odds that people create by their betting do not have a lot necessarily to do with the likelihood of a horse winning. I mean, you might say either you win or you don't, 1-1 and none didn't. All that's true. It's all about guesses people make and how they're willing to put their money where their mouth is and try and make some money because they think they know more than others. Same as going on in the stock market. But anyway, if a horse is 9-1 shot, what's the probability of winning? I didn't say here if 9-1 is in favor or against. But the standard thing that you'll hear at the racetrack, if it's 9-1, will be the odds against. So this will be 9 losses and 1 win. Add them together, you get 10 total. And now probability is the probability of winning. Unless they go out of their way to say anything else, what's the probability of it winning, right? Like it says there. You want to put your wins, 1. Probability of a win is 1 over 10. It's based on 1 win and 9 losses, giving you a total of 10. Put your winner of 1 on top because it's asking about the odds to win. And put it over the total, and there you have probability. So the deal of what has to happen with odds related to probability is if you're given the odds, you know 2 numbers for wins and losses. And you use that to find the total to put together with a probability for what they're asking for. If you're given the probability, you're given a total and you're given either wins or losses, good or bad, in favor or against, right? And use that to find what's the missing number. I don't know which it'll be because it depends on the problem, but find the missing number and then give them what they want in order that they requested it. In favor is wins first, against is losses first. All right, now we're going to look at something called a sample space. If you're watching these in order, reading the book and stuff like that, you will have heard of sample spaces already. But I'm going to create some sample spaces for us. Sample spaces, you can find them in the book if you bought the book, online in the book if you're looking in section 10.4. If you go through the textbook that's online, that's where you can find section 10.4, where you can find the sample spaces I'm going to create and others that you can use as standard sample spaces. I'll likely email them to you as colored sample spaces. You can print them in color, you can print them in black and white if you'd like. If you're watching this and I haven't emailed it to you yet, please don't expect someone else to do it. Email me and say, can you send us the sample space? I've got it in digital form. I just want it to come to you at the right time in the semester. I don't want to pile stuff on you and have a big bunch of stuff that you don't know what to do with it. So if I haven't sent you the sample spaces yet, ask me to do that, and they'll come to you. You can print them in color, you can use them in black and white, you can look at them on your screen. I'm going to create them here because I think it's important to get a sense of where they come from. But sample spaces, as we know, represent all possible outcomes in an organized way. If you don't, you don't want kind of when people do their math in like a circle, it looks like, you know, the radar or a hurricane, and they expect me to say, oh yeah, I see what you're doing. That's terrible, right? I can't see what they're doing because it might make sense to them, but if we go in an organized way, then we can all see where patterns develop and things like that. So rectangles are very important when you're doing a sample space. Order is important when you're doing a sample space, because you don't want to go through and say, you know, what are the sides of a die? Well, there's a 6 and a 5 and a 3 and a 1 and a 4. I guess there's only 5 of them, because I forgot the 2. You go 1, 2, 3, 4, 5, 6, and now we stop because that's as high as it goes. You got an order, and then you got something to work with. So it's about doing it in order instead of hoping you catch them all in your one pass through randomly. So I want to set up a sample space for toss 2 coins. What we'll do is we will have, I'll use red and green. We'll have a quarter. And we'll have a dime. Now, I will use the colors to represent what goes there. I can also do this in order. Let's say I toss the quarter first, right? If I toss the quarter first, it can come up heads. And maybe after tossing the quarter, I toss the dime. The dime also comes up heads. Or I can toss the quarter, and the quarter comes up heads. And the dime comes up tails. Now what I've decided is this first column, it's a short column, as when the quarter is heads, it's in this column. You can go heads, heads, and heads, tails, and that's in order. So that is a permutation because of what's about to happen. The quarter comes up tails, but up here all the green ones are heads, so that's TH, that's tails, then heads. And the quarter comes up tails, and the dime comes up tails. That's a sample space. I use different colors. I have the orders of them. Here are 4 possible ways these things can turn out. But if I say, what's the probability that it comes up with 1 heads and 1 tails? Right? You got 4 possibilities of what might happen, but it turns out that 2 of them have 1 heads and 1 tails. 2 others have them matching each other. This is what's going on in the sample space. Is I didn't just say, well, it's possible to have both heads, it's possible to have both tails, it's possible to have 1 of each. So there's 1/3 of each. That's not the case. What you're seeing is half the time you get heads on the quarter, half the time you get tails on the quarter, 2 out of 4. Half the times you'll get heads on the dime, half the time you get tails on the dime. Again, 2 out of 4. But what does it do when they get together? 2 times 2 gives you 4 possible outcomes. Multiplication of that to generate a sample size of 4. So we need our sample space to go like this, because if I say, what's the probability the first one was heads? Well, if you go with this, you know, the first one, we'll call it the quarter, right? Heads and heads here, tails and tails there, 2 yeses, 2 nos. So the odds of it are what people would call even money. I didn't ask about the odds. What's the probability, right? 1/2. Right? You could have 2 places where the quarter came out heads and 2 came out tails. That's 2 versus 2, reduce the fraction. Even money, 1 to 1, right? In favor or against, the odds will both be 1 to 1 that way. But what's the probability that it comes up with heads first? What's the probability that it's a pair of the same thing? Okay, that's a pair, that's not, that is. So it's 1, no, no. It's 2 out of 4 half the time. It's a pair. They don't have to be a quarter and a dime, but they want to be distinct. You want to be able to tell them apart, or you want to toss one to the left and one to the right. You want to label them in their own way. So if you're tossing 2 dimes, you don't want to toss them both in the air together and say, oh, look, there's one of each. Because then you don't know which one of these you got. Having them be a dime and a quarter, helpful. Having them go in different directions where they don't come near each other, also helpful. So you can represent all the things that come out. That's what the sample space needs to do. So what I want to do right now is I want to go ahead and ask a couple questions about these. When I say that I throw 2 coins in the air, what's the probability they're both tails? Do they have to both be, can they both be dimes or whatever? Yeah, but you better come up with a sample space like this. And there you have 4 possibilities. The bottom of the fraction is 4, and probability both tails. I like to think that the easiest way to set up a probability is get that 4 in there first. How many of both tails? Nope, right away. Nope, right away. Nope, by the end, and yes. So 1/4. Wait, what does that mean? If this were to happen, and I were to play it all the way through, I knew as soon as the first one hit his heads, it's not going to both be tails. Same thing here. If this were what my destiny was, as soon as that one hit, I would know it was. On that one, I would say, okay, 1 is done, we're still alive to have it happen, and then we would come to this one. But there were 4 things that came as possibilities there. Probability of 1 of each. Four on the bottom. No. The first one that does work. The second one that does work. No to that. You get 2 out of 4 half the time. They don't match. It doesn't matter what the first one does. Half the time you're going to match it with the second one. And that's why it reduces to half, but 2 over 4 will do just fine for us. Now I want to set us up to deal with a deck of cards. So what we're going to do for a deck of cards, it's made up of 52 cards, not 54. You buy 54, it includes some jokers, 2 jokers, maybe some other stuff in the deck as well. Let's see what we have. I sure hope I'm not stuck using the middle bit. I will if I have to. Alright, little small deck. No big deal. Terrible pun. Okay. I have 52 cards here. I can lay them out, but I have these set in a certain way. There are diamonds. This is the 9 of diamonds. Okay. There are spades, which look like black hearts with a little stem coming out of them. That's the 2 of spades. Hearts look like Valentine's, not like the organ, right? That's a 6 of hearts. I haven't shown you the clubs yet. I know cards pretty well. Don't ask why. Well, you can ask. I can tell you, but it's fine. It's a club. That is the Queen of Clubs. That had a face on it. What I'm going to do is I have 52 cards here. I'm not sure why. I'm going to take this, and I want to show you what's going on. Let me just make sure. Yeah, here we go. Ace functions like a 1. 2 or deuce is the 2. These are all clubs. 3 of clubs. 4 of clubs. I'm going to count on up 5. It actually gets to 10. 6, 7, 8, 9, all clubs, 10, Jack, okay, that's the young man in the deck, Queen, the only woman in the deck for the clubs, and the King, the old man, okay? Don't get me started on the patriarchy, but the ranking of cards is from numbers. Now, aces are tricky. They can be the lowest card, and they also get to function as the highest card depending on the game you're playing. Aces are a little weird, but they would be as 1. Okay. We go from 1 to 10, and then we have the young man, Jack. We have the lady of the court, the Queen, and they said back then that the King is the highest ranked card, depending on what you do with an ace. Let's go with 1 through 10, right? Count from 1 to 10, that's 10 cards. We know how to count from 1 to 10 and get 10. Jack would be the 11th, Queen would be the 12th, and the King would be the 13th. So there are 13 cards that have clubs on them. In the deck, we have the same thing. I'm going to use 4 colors for this, okay? I'm going to set up the clubs first. All right. So with the clubs, we got the ace, and the 2, and the 3, and the 4, and the 5, and the 6, and the 7, and the 8, 9. For 10, I'm going to put a T. I don't want to have a 2-digit number. Then the Jack, the Queen, the King, and I already have the ace down here. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's T for 10, 11, 12, 13. That's my clubs. We have something else that's dark also, which is called the Spades, and they have the upside down black heart with the stem coming out of it, and they have the same stuff. So it's uniform how each suit is going to be working through here. Now we got hearts. Those that look like Valentines, they're red, and they look like upside down spades with no stem. You hardly hear it that way ever, but they're going to do the same thing. Jack, Queen, King. I haven't used green yet. I reserved that for the other thing that's normally red in the deck, and that's diamonds. You know, they look like skinny squares that are tipped sideways, but anyway, right. Ace, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, 13. There's our whole deck. Anything we want to do with our deck of cards can be represented among those 52. What do I like to say about the jokers? I like to think that when you bend a card or lose a card, you can take the joker and write on it gently what's the rank, which is either the number or the face or the A for the ace of who gets it, right? J key. See, the King has the K in the corner, Queen has the Q in the corner, the Jack has the J in the corner, even the ace has the A in the corner. Well, I didn't need to go to that one. The A in the corner. 10 doesn't have a T in the corner, it has the number 10. I just didn't want to have anything represented by more than one character. Because if we look among, once we decide what we're dealing with, those items, we can see that there are 13. I'll use pink to represent this. This is where the aces, the twos, pink is a little too red for me. We'll go for maybe orange, will give us a little more of a blend. In there for me? Yeah, always count on orange. We have our places here. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, and King. What happens is orange will represent what's called the rank of the card. Every card has a rank, and every card has a suit. There are 4 suits: clubs, spades, hearts, and diamonds. There are 13 ranks that go from ace to 10 with Jack, Queen, King. 13. If you're multiplying this 4 by that 13, you get the 52. So if I were to count those 52 cards out for you, here, I'll get it started. 1, 2, 3. I'm not going to do the whole thing, okay? They're not going to come out necessarily in that order, but they're all in there, which means when I go and cut this deck, I don't know what's coming up. I'll show it to you now. It's the King of Diamonds. There's one space in there that represents the King and the Diamonds. It has to be where the Kings go, and it has to be where the Diamonds go. So because it's where the kings go, it's over here on the last column. Because it's where the diamonds go, it's over there. I randomly drew the card in the far right corner. Do another one for you. Ace of Spades. Ooh, the death card. That's pretty weird. It's up in this corner. That really happened though. So I didn't really get anything that I was looking for to have maybe be a little middly. 2 of diamonds, not very, right there. And do this, all 52 cards are in there. Here we go, this might do it. 6 of Spades. But where the spades are, somewhere in there lies the 6 of Spades. Among them is only 1 6. Or somewhere among the 6s, only one of them lies as a spade. So every card has 1 spot in there, 52 cards in that sample space. That's our sample space for a deck of cards. I'm going to go blue and red. This is usually more fun in the classroom to deal with for the rolling of 2 dice. By now we might be familiar with the fact that rolling a single die has 6 ways it can turn out. But I have dice of different colors. So I'm going to say I have a red die and I have a blue die. And I want to represent what they can do. So let's say the first die can be a 1. And I'm going to put that down here for some reason 6 times. Okay? The red die can be a 1. The reason for that is the blue die can be a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And therefore those look like 11, 12, 13, 14, 15, and 16. And that's what they'd be called if we had them in colors. Dice when rolled together often don't come in colors, but this will represent 11 through 16. And I'm not going to have the exact same number that I call as 2 digits showing up again. Now, I want to do the 2s. I'm going to spread it out a little bit. I'm going to do 1, 2, 3, 4, 5, 6. That's when the red die is a 2. And I'm going to go 1, 2, 3, 4, 5, 6. And that represents 21 to 26. Numbers got skipped, but they give them names this way when I put them into my sample space. Okay. Now what you're going to see is I'm going to set up a row for a column of 3s, a column of 4s, a column of 5s, and a column of 6s. So I'll go ahead and put down all my 3s. 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 2, 3, 4, 5, 6. Okay, all my reds are taken care of. Now I'll put my 1s on the top row, my 2s on the second row, my 3s on the third row. I'm doing the blues now for second digit. 4. They got a little misaligned. Lined paper is awesome. 5s and 6. They're not out of order. They may be a little misaligned, but they're all there. There are 36 of them. Lined paper, like I said, is awesome. The sample space I'll be sending you will be good for that too, because they line up nicely. Those are sample spaces. This is 2 dice being rolled. Now, when dice are rolled, one of the most important things that they do with them is they look at the total that they add up to, the sum. When I play dice, right, and I want to get an 8, and it rolls 4 and 2, I might jokingly say to them, can't we just multiply them? It never works. But 4 times 2 would get me the 8 that I needed. No, they're always added together. So the sum of what the dice make seems to be what people are interested in. And so here are 36, right? We've got 6 here, starting with 1s, with 2s, with 3s, with 4s, with 5s, with 6s. 6, 12, 18, 24, 30, 36, 6 at a time, whether you want to go counting 6 across, going down 6 each time as you go down, or 6 across, as you go across, kind of 6 times 6, 36. That's the bottom of our fraction when we're doing a probability rolling 2 dice, looking at their sums. 52 is going to be 4. The orange doesn't count. That's just labeling, just like the word spades, clubs, hearts, and diamonds do here. Creates our 52 for our sample space. Those are our sample spaces that we use frequently. And so I want to get some probabilities for you here. Let's get some probabilities, dice probabilities. Two dice probabilities dealing with sums. It's find the probability of getting a 7. I'll put them all up here. You can stop the tape, the recording, when you figured it out, and then try and complete the rest of them. You can watch most of them, try the last one. You can watch the first one, try them all, whatever you want to do. But I'm going to show you the process of each one in its order, and you can make as much use of the video to help you figure it out as you need until you've got it on your own. So if you get 2 in a row right while you're watching the video, try the last few. Probability of getting a sum of 11. Let's see if I can get a better marker here. Probability of the sum of 2. Yeah. Probability of the sum is 3. Yeah. Probability of the sum of 12. Okay. Let me get the first one done. The probability that the sum is 7. Because I have a good sample space, where the 7s are should form a pattern. I don't know how well I drew it without lines, but we'll see. All right, there are 36 dice outcomes possible there. I'm going to find the probability of getting a 7. Let's see. Red 1 and a blue 6, 16, 25, 34, 43, 52, 61. Let me look at the red number to count them. 1, 2, 3, 4, 5, 6. There are 6 ways. Now, how do I think about that? I mean, I've spent some time, I won't say how much, at dice tables to recognize that no matter what the first die is, the second die can make it a 7. If it's a 1, a 6 can come along. If it's a 6, a 1 can come along. And anything in between can do it. So no matter what the first die lands on, if they were to roll them separately, which they don't allow, you could make a 7 if you get the right thing on the second die. It's not an impossibility. Turns out to be 1/6, but 6 over 36 can be helpful for your thing. Okay. So now, the next question, if you're not so sure about probability, would be for you to individually decide. And I'm going for the probability of 11, total of 11, sum total of 11. How many are on the bottom? Again, 36. 6 over 36 is functional and fine for your probability. All right, how about 11? Where's the first 11? If I roll a red 1, can I make 11? No, there's no 10 on the blue dice. How about a 2? No. Because you look at the bottom, that's a 7, that's an 8 when I add them. So it turns out that if I roll a 3 on the first die, or a 4 on the first die, since there's no 7 on a single die, I can't make 11. Until I at least get a 5 on the first die, where I get this 56. And then there's one over here where 65 is. It's just those 2. 2 out of 36. Probability of rolling a 2. It's a total of 2. That's an interesting proposition, because if you roll them separately and you need to get a total of 2, the first one has to be a 1. Has to. There's no 0 or negatives on the die, so you got to get a 1 on the first before you even roll the second one, which also must be a 1. The only place that happens is up here. The other 35 are no good, so it's 35 to 1 odds against this happening. But again, it's 36 for the probabilities denominator. One of those. Okay, now might be a time where you're saying, okay, I think I sort of get this. You might want to try the 3 and 12 on your own, or you might want to wait for me to do the 3 and go after 12. I'm going to go ahead there. 36. Find the 3. If I roll a 1 on the red, I can get a 2. If I roll a 2 on the red, I can get a 1. If I roll a 3 on the red, I can't. I only have these 2. Out of 36 possible rolls, only way is to get a red 6 and a blue 6. Having the dice of different colors is very helpful. Most of the time you're rolling dice, they are the same color. But this lays out for us what we can look at for our values to take a look and see what's happening in this sample space. Why are these numbers important? You can skip over this when you see me writing some other stuff. You can come back. But I want to tell you, these are the key numbers that come out in the game called craps at the dice tables in the casino. And that is, what goes on is this. You put down, let's say, your bet of $1, and the game has begun. And then maybe you roll the dice, or maybe someone else does. If it shows up as a 7 or an 11, then you win instantly. You get your money for not losing, and you get the same amount of money for having won the bet. And what that is these guys here, 6 and 2, 8 times out of 36, there's an instant win for you. This one, if it comes out a 2, a 3, or a 12 on the first roll, that's an instant loss for you. But that's not too bad because there's only 1 plus 2 for 3 plus 1 for 4. 4 out of 36 times that you lose right away. So what happens is if it's going to be won or lost on that initial roll because it's a 7, 11, a 2, 3, or 12, you're going to win 8 times and you're going to lose 4 times. That sounds pretty good. But if none of that happens, the dice come up as something else, right? And they can be, if they're not 2, 3, 7, 11, or 12, they could be 4, 5, 6, they can be 8, 9, 10. If any of those shows up, what they do is they put a little thing that looks like a hockey puck, and it's called a puck, on that number on the board, and a race has begun. Your bet is still committed to the game. You can't say, oh, I lost, too bad, I'll see you later. No, now you're stuck in the game until the race is over. The race is that you're going to hit the number with the 2 dice in a succession of rolls. The race is 1 if you hit the number again. That's why it's called the number, also known as the point. But you're racing against the 7. This 7. The 7 is the one that has the most chances of occurring. It occurs 6 times. If you want to look at the 5, if you want to look at the 6 and the 8, they occur 5 times. If you want to look at the 5 and the 9, they occur 4 times. If I look at the 10 and the 4, they occur 3 times. I mean, this other stuff doesn't hurt you anymore. Okay, 11s don't help you anymore. 2, 3, 12 don't hurt you anymore. You're in a race against the 7. And the 7 is always a favorite once it goes to a point. And this has been calculated out as a very tempting game for some people, but if you play it right, you just bet on it. The house has about a 1.4, I think, percent advantage over you. That means that if you were to bet $1,000 throughout the course of the afternoon, you kept betting, you stayed, you played 1,000 times, and everything came out the way it was supposed to, you would lose about $14. So, that's probably a very long day. They don't let you play for $1. You might have to play for 10, right? But you'd still get 100 games in for your $10 each. And you'd think, I need $1,000 to play this game. No, not really. You just have to have $10 to put up each time, but sometimes you're winning, sometimes you're losing. The expected amount of the way things is going to go is when you bet $1,000 this way through the game, is the overall expectation is you'll lose $14. So if you bet $1,000 on it the first time, you're either going to lose $1,000 or win $1,000 in that game, and that's it. If you bet $10 a time, you're going to play 100 times, and there's an anticipation of you losing $14. If you bet $1 each time because they let you, over the course of the time that you do those 1,000 games, they think that you're going to lose about $14. Because so many people are playing for so much money for, with all the different tables and all that, they use that advantage to make money. They want lots and lots of people to play. They want people to spread the money evenly, just like in sports betting, and then they want to make some money on that. So let's have you now do one. Find the probability of rolling a total of 8. Okay. You can stop now if you want to do the whole thing yourself. I'm about to take the easy part anyway. Where are the 8s? Where do the 8s begin? I can't make an 8 here, so I don't even get my counting. But the first 8 I come across when I look down here is 2, 6, 35, 44, 53, 62. I found 5 8s. 5 out of 36. So on one roll of 2 dice, what are the odds against you rolling an 8? 36 is the total. 5 are successfully going to be 8. Odds against an 8. You can look back to try and determine odds yourself. Maybe you remembered it. Try and find the odds against an 8. Total. Wins. Losses. Which doesn't mean you lose your money right away. It just means it didn't come up as an 8. 31. 31 to 5. That doesn't even reduce 31 over 5. You wouldn't turn it into something like, 6 and 1/5. It is more than 6 to 1, that's true, but 31 to 5 would be the odds against rolling an 8. So that's how the odds go. All right, give you a couple more. Find the probability of drawing a card that's a spade. Cards where there are 52, get started. Again, stop the tape as you want to, but figure out how many spades are in there. Find the spades in the blue row where there are 13. You can count them by hand if you want. That is a successful setup of the probability. That does actually reduce to 1/4. Because the cards are evenly distributed into 4 suits. One of the 4 suits is a spade. Probability of getting a 9. Not total 9. This is not on the dice, it is the deck of cards. Probability of landing on a 9 with the 52. Successfully completed with 4 out of 52. There are 4 of them, don't count the orange, which is telling you the label, but there's 1, 2, 3, 4 9s among the 52 cards. That does reduce to 1 out of 13. If you look at any one of the rows, let's take the red heart row and say, this is a representation of uniformly how they're distributed throughout the deck. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards that are the hearts, and one of them is the 9. I successfully have 1 out of my 13. That's the reduced fraction gets you because of the uniformity of the way the deck is laid out. So that gives you an idea of how this works for some of these. And you'll see some in the homework that are dealing with roughly the same idea. But again, if you're getting past this and you haven't yet received an email, please email me and ask me to send you a copy of the sample space, and I'll just fire that right off to you. And you'll have that to work with. And you'll see some more in the homework to get with, but this is the concept set that we're working with right now. Okay.